Welcome dear learners. We are continuing the course Quantum Chemistry. In this module, we are discussing postulates of quantum mechanics. The module is aimed to familiarize the state function postulate, well-behaved functions, normalization, orthogonality condition, orthonormality of wave functions, and the Born interpretation of wave function. First of all, the postulates of quantum mechanics. In order to understand deeper quantum mechanics, scientists have derived a series of axioms that result in what are called the postulates of quantum mechanics. The postulates of quantum mechanics are similar to the beliefs of a religion. If you want to follow a particular religion, you have to follow the basic rules of that religion. Similarly, if you want to follow quantum mechanics, we have to follow the postulates of quantum mechanics. It is important to notice that the postulates are necessary for the interpretation of the theory, but not for the mathematics behind it. The first postulate of quantum mechanics. The first postulate of quantum mechanics is known as the state function postulate. Let us go to the statement of the first postulate. The state of a quantum mechanical system can be completely specified by a function psi of rt that depends on the coordinates of the particle and on time. This implies that according to the state function postulate, we can describe a quantum mechanical system completely based on a mathematical function called state function. The state function psi depends on two parts. The first part is R, simply designate the coordinates, and T represents time. This is the statement of the state function postulate. Now, what are well-behaved functions? In the state function postulate, we heard about the state function, that is psi of rt. It should be noted that the state function psi of rt is a mathematical function. It may be just like e raised to ix, sin x, cos x, tan inverse x, etc., etc. But all mathematical functions are not accepted as state function. What is the reason? In order to accept a mathematical function as a state function, it must have some qualities. In other language, we can say that a mathematical function is acceptable as state function one and only if it is well behaved. That means only well behaved mathematical functions are accepted as state functions. For a function, for a mathematical function to be well behaved, it must satisfy some important conditions. There are four important conditions for a mathematical function to be well behaved. The first one being that the function must be single valued. That is, the mathematical function under our consideration must be single valued. The second one, the function must be continuous. The function must be finite. And the last condition, the mathematical function is already normalized or it can be normalized. So, single valued, continuous, finite and normalized are the four important features for a mathematical function to act as a well-behaved function. And only well-behaved mathematical functions are accepted as state functions. Now, what are single valued functions? In a given region of space, the wave function must be single valued. This implies that there is only one probability of finding a particle. We know the fact that the probability is psi square. That is, square of the wave function gives probability. For a single valued function, there is only one value and the square of which is also having only one value. That is, there is only one probability of finding a particle in a particular region. The example for a single valued function is sin x over the limit 0 to pi by 2. It should be noted that within this limit 0 to pi by 2, sin x is having only one value. That is, sin 0 is equal to 0 and sin pi by 2, that is sin 90, that is equal to 1. So, the function sin x is a single valued function, especially over the limit 0 to pi by 2. Now, a question arises. Explain why the function sin inverse x at x is equal to 0 is not acceptable as wave function. This can be correlated to the single valued nature of the function sin inverse x at x is equal to 0. We can move on to the details of this function and we can prove that the function sin inverse x at x is equal to 0 is not a single valued function. We can proceed like this. We have sin n pi is equal to 0, where n is equal to 0, 1, 2, 3, etc. Sin 1 pi is equal to 0, sin 2 pi is equal to 0, so and so, where pi represents 180 degree. Sin n pi is equal to 0. I can put inverse of sine on both the sides. Therefore, sin inverse of sin n pi is equal to sin inverse 0. Sin inverse sine will vanish and we will get n pi is equal to sin inverse 0. Or simply we can say that sin inverse 0 is equal to n pi. This is an important result. Now come back to the given question. The given question is about sin inverse x at x is equal to 0. That means I can replace this x with the 0. Therefore, at x is equal to 0, the given function is sin inverse 0. And we already learned that sin inverse 0 is equal to n pi. Sin inverse 0 is equal to n pi means it may be 1 pi, 2 pi, 3 pi and etc. So, there are more than one values possible for the function sin inverse x at x is equal to 0. This implies that the given function sin inverse x at x is equal to 0 is a multi-valued function. A multi-valued function cannot be accepted as a state function. That is why sin inverse x is not acceptable. Moving on to the second condition for well-behaved nature, that is continuity. Then what is a continuous function? The probability of function does not have discontinuities. The probability must be continuous. Thus, the acceptable wave function must be continuous. For a function to be continuous, all first order derivatives of the wave function must be continuous. This continuity can be inferred from the graphical representation. Consider the function e raised to minus x over the limit 0 to infinity. It should be noted that this function e raised to minus x within this limit is a continuous function. This is inferred from the graphical plot of this function over the limit 0 to infinity. In this graph, we can see a continuous nature. There is no discontinuity is observed. Also, its first derivative is continuous when plotted graphically. Thus, for a function to be continuous, the function and its first derivative must be continuous, especially when plotted graphically. That means there should not be no discontinuity observed in the graph. Now, the third condition for well-behaved nature, that is finiteness. What is meant by a finite function, or what are finite functions? It should be noted that the probability associated with a quantum mechanical system ranges from 0 to 1. This implies that the minimum probability is 0 and the maximum probability is 1 or 100%. This implies that the wave function under consideration must be finite. Simply means the wave function shouldn't have values like infinity, 1 by infinity, infinity square, 1 by 0, etc. etc. Now, the last quality for a function to behave as a well-behaved function, that is normalization, or the given function must be normalized. Now we are discussing what are normalized functions. Condition for normalization. It should be noted that the normalization is a mathematical condition. And now I am representing the condition for normalization. This is the condition for normalization. Integral minus infinity to plus infinity psi star rt psi of rt d2 must be equal to unity. This is the simplest mathematical representation for a function to be normalized. If the given function psi of rt satisfies this condition, we can say that the given function is normalized. Now we can move on to the details of this. First of all, what is the difference between psi of rt and psi star rt? It should be noted that psi star rt is the complex conjugate of psi of rt. What do you mean by the term complex conjugate? We are familiarized about the complex number, that is root of -1 or I. If in the given state function, if there is a mathematical quantity I or complex number I, to get to the complex conjugate, we have to replace I with -I. For example, let the given function psi of rt is I cos x. Then its complex conjugate psi star rt will be equal to -I cos x. Another example, e raised to -x, if it is the given function, then its complex conjugate will be e raised to ix. This means if the complex number is appeared, it should be replaced with -I to get to the complex conjugate. Similarly, if there is a function without any complex number, then psi of rt will be equal to psi star rt. Such functions are called real functions. For example, if we have psi of rt is equal to sin x, then psi star rt will also be sin x. This is because here there is no complex number to replace. Thus, we familiarized psi of rt and psi star rt. Now we can move on to the details of this integral. This element d2 is a product of three terms, that is dx into dy into dz, that is d2. If I replace d2 with dx, dy and dz, I must replace this integral by volume integral or triple integral. Therefore, the complete expression for normalization is integral, integral, integral. This is the volume integral or triple integral. In all the directions we are integrating, that's why we are having the volume integral. And the limit of integral in all the spatial directions x, y and z will be from minus infinity to plus infinity. So the limit of integral from minus infinity to plus infinity along x-axis, minus infinity to plus infinity along y-axis, minus infinity to plus infinity along z-axis, followed by triple integral of psi of rt star, that is psi star rt, into psi of rt. Then I replace d2 with dx into dy into dz is equal to 1. This is the mathematical condition for a function to be normalized. In order to accept a function as normalized function, we have to follow this mathematical condition. If on integrating the RHS is equal to 1, we can say that the given function is already normalized. In many cases, we are changing the limit also based on the system under our consideration. If limit is not specified, the limit is from minus infinity to plus infinity. Therefore, on the basis of all this, the simplest way of representing condition for normalization is integral psi star rt psi rt d tau is equal to 1. If integral limit is not specified, it is implied that the limit of integration is from minus infinity to plus infinity. This about the normalized function. Now we can move on to another part. For instance, if the given function is already not normalized, then there is a possibility to normalize that function by introducing suitable constants. Such a procedure is called normalization. So we are moving on to another part, that is called normalization of wave function. If the given function is already not normalized, by incorporating some suitable constants, we can normalize that function. The procedure we adopted here is known as the normalization procedure. How to normalize a given function? First of all, we are trying to evaluate, we are proceeding like this. Let the given function is psi of rt. Find out its complex conjugate as psi star rt and proceed accordingly by the condition for normalization equation, that is psi star rt psi of rt d tau. We are now evaluating the integral. If the limit is not specified, I already mentioned that the limit of integration is from minus infinity to plus infinity. So, if the given function is already not normalized, then we have to evaluate this integral first and look the final result of this integration. If the result of this integration is a constant value, then only we can normalize the function. If this integral result is not a constant but a variable like x, y, z or any function, we can't normalize the given function. So ensure that if the given mathematical function is not already normalized, there is a chance for normalizing it if and only if this integral must be equal to a constant, and let that constant is capital N. Then the normalization is made possible by multiplying the given function psi of rt with 1 by root n. That is reciprocal root of the constant obtained as a result of getting this integral. So I will explain the procedure by taking some numerical example. Before proceeding to the example, this is the mathematical strategy. The strategy I will explain once again. The condition is like this. Let the given function is already not normalized, then only the normalization is relevant. We can normalize the function if and only if On evaluation of this integral, if we will get a constant n. Instead of this constant, if you are getting some other functions, there is no chance for normalizing it. So, first take the function, evaluate this integral, look for its result. If you are getting a constant n, then multiply the given function with the reciprocal root of the constant obtained after integration. This is the procedure for normalization. Now, we can take some examples for normalization. The problem, normalize the function e raised to ix over the limit 0 to pi by 2. Repeat, normalize the function e raised to minus ix over the limit 0 to pi by 2. From the question, it is clear that the given function e raised to ix is already not normalized. That's why the questionnaire asks for doing normalization. Therefore, we are moving on to the procedure for normalization. The given function is psi of rt equal to e raised to minus ix. Now take its complex conjugate. Therefore, we are getting psi star rt equal to e raised to, I replace I with the minus I, minus vanishes, so I got e raised to ix. Then I am going to evaluate the integral, and in the problem it is specified that the limit of integration is from 0 to pi by 2. So integration is performed over this limit, integral 0 to pi by 2. First function psi star rt, that is e raised to ix into e raised to minus ix. d2 is not required because we are having only one variable. Therefore, d2 is simply reduced to dx. Now we are going to evaluate this integral. This integral is simply integral minus infinity to plus infinity psi star rt psi of rt d2, that is changed to this for the present problem. In the present problem, the limit of integration is from 0 to pi by 2. Psi star rt is e raised to ix, psi of rt is e raised to minus ix, and d2 is diminished to dx because we are dealing with the one variable, that is x. On integration, we will get some value. This a raised to m into a raised to n, a raised to m plus n. So, the result is like this, integral 0 to pi by 2 dx. That is, integral dx is equal to x. Therefore, x, the lower limit is 0 and upper limit is pi by 2. Therefore, the limit, after applying the limit of integration, we will get the final value of this integral as pi by 2. So, I evaluated the integral psi star rt psi of rt d2. Its value is pi by 2. No doubt, it is a constant. Therefore, we can normalize the function e raised to minus ix. This normalization, how the normalization is now possible? And this integral, this result of this integration is n. And we have to multiply with the reciprocal root. So, in the present problem, the constant obtained after the integration is pi by 2. Therefore, to normalize the given function e raised to minus ix, we have to multiply with the reciprocal root of the constant obtained after integration. That means e raised to minus ix must be multiplied with the reciprocal root of pi by 2. That is under root 2 by pi. Under root 2 by pi. Hence, it is sure that the function root of 2 by pi into e raised to minus ix is perfectly normalized function. Now, if we are performing the normalization condition with this function, definitely we will get integral result equal to unity. That we can also prove. So, once again, normalization of wave function is under consideration. Now, it should be noted that we have to evaluate the integral and look for the constant result, then multiply reciprocal root of that constant to the given function to make it normalized. This is the condition for normalization, and this is a typical example for the normalization procedure. Now, we can prove that this function is normalized now. So, how is it possible to prove it? Just perform the again integration with the limit by taking this function. This is now the normalized psi of rt. Then take its complex conjugate to get psi star rt as root of 2 by pi into e raised to minus I is replaced with the minus I. So, e raised to ix, this is psi star rt, this is psi star rt. We can now perform integration by using this psi and this psi star rt within the limit 0 to pi by 2. Now, we will get a result like this. Integral 0 to pi by 2, 0 to pi by 2. Psi star rt is a root of 2 by pi into e raised to ix multiplied by psi of rt, that is root of 2 by pi into e raised to minus ix. Limit d2 is replaced with the dx, and we can perform this integration. Root 2 by pi, root 2 by pi multiplied together to get to 2 by pi, that can be taken outside the integral sign. So, 2 by pi into integral e raised to ix into e raised to minus ix dx within the limit 0 to pi by 2. On performing this integral, we get the value as pi by 2. So, the result is equal to 2 by pi into integral 0 to pi by 2 dx. Integral 0 to pi by 2 dx we already evaluated. Its value is equal to pi by 2. So, 2 by pi into pi by 2, that is equal to 1. That means the wave function root of 2 by pi into e raised to minus ix satisfied the condition for normalization. Therefore, this is the clear illustration of normalization procedure. Now, another simple problem, we can proceed in a similar fashion like this. This is another function, e raised to I to x over the limit 0 to pi. That is, we have to normalize another function, e raised to I to x over the limit 0 to pi. Proceed similarly as in the case of the previous problem. We can move like this. Let the given function is psi of rt. Psi of rt is equal to e raised to I to x. Similarly, complex conjugate psi star rt is equal to e raised to minus I to x. Now, evaluate the integral between limit 0 to pi by 2 psi star rt, psi of rt dx, because here having only one variable, that is x. Therefore, e raised to minus I to x into e raised to I to x into dx, and this is equal to integral, the limit of integration is from 0 to pi only into dx. So, we are getting the final value as the result of integration of dx, that is equal to x. Lower limit is 0, upper limit is pi. So, the value of the integral is equal to pi. Again, the result is a constant, that is pi is a constant. That is, we have to multiply reciprocal root of the constant with the given function to get it normalized. Therefore, the reciprocal root of the constant is 1 by root 2 pi. So, 1 by root 2 pi to be multiplied with the e raised to I to x to make it normalized. Therefore, the given function is normalized by multiplying with 1 by root pi. And this constant is known as normalization constant. The constant that we have to multiply with a given function to make it normalized is known as the normalization constant. Here in the present problem, the normalization constant is 1 by root pi. Now, this is the wave function for a particle in one-dimensional box problem. The particle in one-dimensional box problem is an important application of Schrodinger wave equation in quantum mechanics. And in the particle in one-dimensional box problem, the wave function of the system is given as psi is equal to a sin n pi by a into x. Here, some conditions to be kept in our mind. This problem can be discussed in coming modules, and in the present case, for the sake of doing the problem, we have to keep some important ideas. The one-dimensional box is having an edge length small a, The wave function for the present problem is psi is equal to a sin n pi by a into x. In the problem, it is given that the wave function is normalized, and it is asked to find out the value of capital A. Thus, in comparison with the previous problems, it can be inferred that the constant capital A is the normalization constant. Therefore, in the present problem, we have to evaluate the value of the normalization constant capital A. By proceeding in an analogous way as we done in the previous problems, the condition for normalization is integral minus infinity to plus infinity psi star rt psi of rt d tau must be equal to 1. Coming to the present problem, the given function psi of rt is capital A sin n pi by a into x. Therefore, psi star rt also same as psi of rt since there is no complex number. Therefore, psi star rt is a sin n pi by a into x. Psi of rt and psi star rt are same. Since we are having only one variable, d tau is equal to dx, and the limit of integration is from 0 to a. Therefore, we can evaluate the integral 0 to a psi star rt, that is a sin n pi by a into x. Psi of rt is also same. Therefore, a sin n pi by a into x dx, and equate it to unity since the given function is already normalized. That is integral 0 to a into a square can be taken outside the integral sign, sin square n pi by a into x dx. This must be equal to 1. This is sin square. If we consider the entire part as theta, sin square theta is equal to 1 minus cos 2 theta by 2. I can make that substitution here to get the result of the integration. The result of the integration can be proceeded like this. Integral 0 to a square sin square n pi by a into x dx. We know sin square theta is equal to 1 minus cos 2 theta by 2. Making such a substitution, a square by 2 into integral 0 to a 1 minus cos 2n pi by a into dx, that is a square by 2 into integral 0 to a dx minus integral 0 to a cos 2n pi by a into x dx. On further proceeding, and we have to equate this to unity since the given function is already normalized. Therefore, on integrating, the second term completely vanishes and will be equal to 0. That you can do in a separate sheet of paper, or a square by 2 into integral 0 to a dx equal to 1. That is a square by 2 into integral dx, that is equal to x. Lower limit is 0, upper limit is a, that is equal to 1, or simply a square by 2 into small a equal to 1, or a square is equal to 2 by a, or simply the normalization constant capital A in the present problem is root of 2 by a. This is the value of normalization constant capital A in the given problem. Here we evaluated capital A based on the condition that the integral is equal to unity, since the given function is already specified as normalized. That about the condition for normalization and procedure for normalization. Now we are moving on to another condition that is called orthogonality. Orthogonality condition is an important mathematical condition that we adopted in quantum mechanics. In order to explain the condition of orthogonality, I have to take two wave functions, two arbitrary wave functions, namely psi I being the first function and psi j as the second function. Now this is the condition for orthogonality. Integral, limit is always from minus infinity to plus infinity if it is not specified. So here also the limit of integration is from minus infinity to plus infinity. Psi I and psi j are the two functions. I am taking psi I as the first function and psi j as the second function for convenience. Now take complex conjugate of the first function. What will be the complex conjugate of the first function? Psi star I. That is the complex conjugate of the first function. Now, psi I star into, that is complex conjugate of the first function into the second function, that is psi j. d tau, that is the integral element d tau, equal to 0. This is the mathematical condition for two wave functions psi I and psi j to be mutually orthogonal. Therefore, orthogonality condition is integral psi I star psi j d tau should be equal to 0. Psi I star is the complex conjugate of the first function and psi j is the second function. You can replace it with the psi I and psi j can be replaced with the psi 1 and psi 2, psi a and psi b, like that. Any kind of notation can be used. Since it is d tau, I cannot split it into triple integral. If it is replaced with the dx into dy into dz, this integral is split into the triple integral. If integration limit is not specified, it is implied that the limit of integration is from minus infinity to plus infinity. That about the condition for orthogonality. Now, we can move on to another situation, that is the coexistence of normalization and orthogonality together. Suppose we are having two mathematical functions, namely psi I and psi j. These are two arbitrary state functions. Then I am going to evaluate one integral. The integral is like this. Integral psi I star psi j d tau. This is the integral. if psi I and psi j are two different functions, if psi I and psi j are two different functions, means I not equal to j, the two functions are different, then the result will be equal to 0. That is the condition for orthogonality. That is the condition for orthogonality. Now, what is the condition for normalization? In this equation, if I and j are same, that is both are psi I or both are psi j, then this integral will be equal to unity. That is the condition for normalization. Then what will be the condition for normalization? Integral psi I star psi I, both are same, I is equal to j, d tau must be equal to 1. This is possible if I is equal to j. This is the condition for normalization. This is the condition for normalization. Hence, we studied two conditions. Condition for orthogonality, that is integral psi I star psi j d2 is equal to 0, provided I not equal to j. And the condition for normalization, I is equal to j, that you can take either psi I or psi j. This is the condition for normalization. Now I am going to merge these two conditions together to get orthonormality function or Kronecker delta. And the Kronecker delta can be represented as delta ij, and there is a mathematical expression for finding out the Kronecker delta, which is the indication of orthonormality. This is Kronecker delta. Delta ij, delta ij, I and j are subscript, delta ij equal to integral psi I star psi j d tau, psi I star psi j d tau. And it should be noted that delta ij or Kronecker delta can have two values. The first value is 0, that is delta ij equal to 0. Delta ij equal to 0. This is possible if I not equal to j. If I not equal to j. If the functions are different, then I not equal to j, and that is the condition for orthogonality. This is orthogonality. This is orthogonality. So, in the case of orthogonality, Kronecker delta, delta ij is equal to 0. Delta ij is equal to 0. Now, another case, that is delta ij can be 1. This is possible if I is equal to j. In this equation, if I replace I with j, that means both of the functions are same, the result will be equal to 1, and that indicated the condition for normalization. So, delta ij equal to 1, that is the condition for normalization. That is the condition for normalization. Hence, we have Kronecker delta, delta ij, which can have two numerical values, either 0 or 1. Delta ij is equal to 0 is possible if I not equal to j, that is orthogonality. And other value, delta ij is equal to 1. This is possible if I is equal to j, that is the condition for normalization. Hence, we can club orthogonality and normalization together to get orthonormality, that is expressed in terms of delta ij or Kronecker delta. Now, the last part of the present module, Born interpretation of wave function. Max Born gave a statistical interpretation of the wave function psi, naming it as probability amplitude function. For this interpretation, Max Born won the Nobel Prize in the year 1954. And the Born interpretation is like this. If psi x is the wave function of a particle, then the probability of the finding the particle within the range from x to x plus dx is given by the mathematical equation px dx equal to psi star psi dx, that is magnitude of psi square dx, where px dx is the probability. This implies that probability is the square of the wave function. The probability to found between the region x and x plus dx is proportional to the square of the wave function. Since total probability of locating the particle must be unity, maximum total probability must be unity, we can also modify the above equation as integral minus infinity to plus infinity to ensure the coverage in the entire space, px dx equal to integral minus infinity to plus infinity psi star psi dx, that is equal to integral minus infinity to plus infinity modulus of psi square dx equal to unity. Thus, in this module, we have discussed the first postulate of quantum mechanics, that is the state function postulate, normalization procedure, and also the Born interpretation of the wave function. That's all about the module. Thank you.